Okay, the solutions for our math practice test on um, the moving straight ahead unit. To begin with, on the screen are some basic concepts about slope, and these are very important, kind of the essential building blocks for the whole unit. We've talked about slope being known as many different things. We've got lots of aliases, from the constant rate of change to the constant proportionality in some circumstances, um, and just simply slope. Um, we've got definitions for slope too. What exactly is it? Of course, we looked at it in graphs. We talked about steepness and thinking of rooftops, that sort of thing, slopes, ski slopes. Um, so we're looking at that when we see visuals, visual representations of slope on a graph. In particular, we've looked at linear equations, so those graphs that pertain to lines. On the screen here, we have some definitions, some specifics of slope. Um, when we looked at the linear equation, which is over here, the linear equation format is y equals mx plus b. That's slope-intercept form. So all the linear equations, all the lines that we graphed, all the equations we wrote and looked at were all in this form. The the y and the x being an ordered pair that represents solutions on that line. The m is the slope, and then the b is the y-intercept, where it crosses the y-axis. Um, what exactly is slope? Well, when we look at a graph, it's rise over run. When we look at an equation, we're looking for m. And we also, in terms of tables, we looked at the change in y over the change in x. And again, that is, think of the change in y, the y-axis, being rise, the vertical, up and down, and the change in x being the run, the horizontal, the x-axis, which is, again, the run. Okay, so keeping some of these things in mind as we go through this practice test, it asks us to find the slope. We can do that. They give us this graph over here. Um, we've got points. So we're just looking, we can take any 2 points we want. It makes sense to take the points that are closest to each other. Oops, it automatically formed a line out of that. Okay, down. Oh, it's a little hard working on this tablet. You'll have to forgive me. Okay, so we got rise over run between these 2 points. Take a look here at the scale. We're going by fives. We got 0, 5, 10, and we're going by fives down here. 0, 5, 10, 15, and so on. So when we look at the, this is bugging me. I'm going to fix this here. Oops, I lost my other dots too. Okay, so when we're looking at rise over run, um, the rise here is between this 5 to 10. So the rise is 5, and the run is also here from 5 to 10. So the run is also 5 units. And that repeats. 5 up and 5 over. 5 up, 5 over. That stair-stepping effect. Now, I don't know who plotted this, but the points don't seem to be the points aren't perfect by any means. They seem to go off their mark a bit there, whoever made this practice test. We're going to assume it is, in fact, a straight line. We're also going to be able to, if that's the case, we'll assume that this next point would be down here at 0, 0. Okay, just completing that line. It is a terrible line. Where if it were truly a nice straight line, it should run. So it should run like that. But anyhow, it is what it is. We're going to, I'm going to keep in mind here, let's see. Slope is rise over run. I always encourage you to write that down. Slope, rise over run. So you can write that down, rise over run. It's also the variable m in the equations. But here we've got, again, it was 5 up and 5 over. So rise over run, 5 up, 5 over. And that's the slope of that line. It's a constant. It repeats and helps form the steepness of this line. We can simplify that to simply 1. Find the equation of the line. Now we're going to be thinking back to what you saw on the first screen. Slope-intercept form is y equals mx plus b. We don't have to fill in the y or the x. We just have to fill in the slope, which is 1. And the y-intercept we said was down here at 0. It's where it crosses the y-axis, which is not labeled here, but the y-axis, of course, running vertically down. Oh, come on, highlighter. All right, so we have y-axis up, y-axis going right on down. There we go. Thank you, smartboard. All right, so y-axis right there, and where our line crosses it is at 0. So we can just put, oops, so working in highlighter, just plus 0, plus 0. We can simplify this. This equation's fine, but we can write y equals 1 times x is simply x plus 0. Well, is the identity property. Just leave it out. So 1 equals x. It's the simplest form of the equation for that line. Moving along, we've got the tables. Now we're going to look again. Let's think back here for a second. Remember we said the important concepts here about slope is it can be rise over run, which is what we just used. Now we're going to look at slope in terms of the change in y over the change in x, this here. We've got a table. Oh, drawing lines too. We want to look at okay, they ask us whether this is a linear relationship or not, whether it's a line. It will be a line if it has a constant rate of change of proportionality. So we'll check that by looking for the slope. And in a table, it's the change in y over the change in x. Again, those are those delta symbols we talked about. This will be our x column. This will be our y column. The change from x to x to x is, they keep adding 5. It's constant. Over on this side, we add 4, and then and then we add 5, and then we're back to 4, and 4, and 4, 4, and then 3. Okay, so I guess it would be worth checking. Yep, these are always 5. So this side is constant, the x, the run. But over here, it is not. So we can't put anything in there for the change in y because it's not constant. So this one is not a linear, does not have a linear relationship. It it actually probably would look something like this, where these points are not on a nice straight line. Perhaps maybe worse. But anyhow, we would say that no, this is not linear because it doesn't have a constant rate of change. It doesn't have a slope here that's constant. Solving equations so that we can, let's say, solve each equation for m. This part of the book was helping us to practice solving equations so that later we can rewrite equations in slope-intercept form. In 8th grade, you'll write them in standard form. So this is, you can kind of think back to the pouches and coins problems that we did, and most people did pretty well in the pouches and coins. Let's do this. What we want to do is get m by itself. So again, if you want to think of this like 4 pouches plus 7 coins equals 51 coins, what we did before is we subtracted 7 from both sides. That leaves us the 4 pouches and the 44 coins on the right side of the equation. Then we can divide by the 4 pouches so we can find out what 1 pouch contains, 11 coins. Over here we've got coins and pouches, pouches and coins. So we've got to get all the coins on one side and all the pouches on another. I would take out the 3. Okay, so on this one, as I was saying, we'll take out the 3 pouches on this side and 3 on this side. That gets rid of those. We're left with 15 coins, if you will. On this side, we're left with 4m, and we have plus 3 coins. Now we'll take out the 3 coins on this side and this side. So we have 12 coins equals 4m, or 4 pouches, which are divided by 4. We find out that there's 3 coins in every pouch. Could you do it other ways? Yeah, I mean, you could subtract the 7m from both sides, but then you'll end up with negative pouches over here on the left side. You can do that and take care of that later, but to me it's easier to subtract the smaller number here from the larger number over here. Same thing with the 15 and the 3. It's easier to subtract 3 from the 15 than it is to subtract 15 from the 3. On part C, we'll distribute the 9 whenever we see a number and in front of the parentheses like that. We can use the distributive property, especially when there's nothing else we can do because we can't add 1 and m together. So we'll distribute 9 times m is 9m plus, they're adding, so we'll add 9 times 1 is 9 equals 24. And then we have a situation that's just like the first problem we did. We'll subtract 9 coins from both sides. That leaves us with 9 pouches, 9m, and we've got 15, and divide by 9, divide by 9. We've got m equals 15 ninths. We can leave it as an improper. We could reduce that, dividing them both by 3. We get 5 thirds. So that's fine. Down here, which of the following expressions is not equivalent to others? Explain. Okay. We're going to, we've got a positive 5 plus 6t minus 6. And again, you can use that keep add opposite if you want to make everything addition, which just allows us, whether you do it in your mind or you actually rewrite it, it allows us to put the constants together. 6t will just stay. There's nothing we can do with that. It's all going to be there by itself. And then we can do plus 5 plus negative 6. Well, 5 plus negative 6 is negative 1. And we can leave that. We can't do anything more. It's as simplified as it gets. Over here, 6t minus 1, nothing we can do with that. And it is also the same as our part A. Over here, we see that we can distribute again. 6 times t is 6t. Subtract, subtract. 6 times 1 is 6. Plus 5. Again, if, well, these are already set up so the constants are right next to each other. If you want to change it to keep add opposite, you can. Negative 6 plus 5 is negative 1. So again, we have 6t minus 1, or subtract 1, or add negative 1 if you want. So this looks just like B, looks just like A. So clearly the 1 is D. That doesn't match. We can prove it by just distributing 6 times 1 is 6, minus, since they were subtracting, 6 times t is 6t plus 5. Using that KAO, you can rewrite this to adding opposite. And again, whether you do it in your head or you write it down, we can shuffle these around a little bit. So we got 6 and 5 is 11 plus negative 6t. Even if I put the t in front, the term with the t in front, I've got plus 11 or positive 11 instead of negative 1 or subtract 1. So D is the odd one out because there's no way we can rewrite the equation or simplify it so that it's like the others. Now we jump back to slope again. This comes back to, go back here for a second. Okay, so we looked at slope in terms of m. We looked at it in terms of rise over run when we were looking at a graph. And now we're going to look at it in terms of change in y over change in x, again with the table. So we'll go over here to our table and pens. Okay, and a thinner pen. All right. let's use red for heck, it's easier to show up. Okay. First of all, they were kind of mean. They stuck this x. You can see it's -2, -1, 1. Really, these, and you can write it if you want. I would just write it in here. 0, 6. So the order is correct. -2, -1, 0, 1. And then I can look here, 0, 3, 6, 9. And I can see the change in x. The change in x, they consistently add 1. -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. So they keep adding 1. Sorry. Change in y over change in x. So for x, we have a positive 1. That's the change. For y, they go 0 to 3 to 6 to 9. So they keep adding 3 each time. So the change in y is 3. So here's our slope, 3 over 1. Over here they do the same thing again. They've got 0 for x, and then 2, 1, -1. So again, 0 and 6. Move that right here. So I can it's just easier to see what's happening. -2 to 1 to 0 to -1. They are each time subtracting 1. And 0 to 3 to 6 to 9, they are adding 3 each time. If we think about change in y over change in x, the slope is 3 over a -1, or -3 if you want to reduce, just like this one over here. Slope, you could call it 3. Over here, slope, you could call it -3. 3 divided by -1. So we've got our slope for both of these. One is positive and one is negative. Really, when we look at the lines here, we could cheat, because we see that this slope on the left is falling. It's decreasing this way. Down, down it goes. That's a negative slope versus slope that you see from left to right. If it's rising, like this one, oh dear, sorry, there we go, rising, then it's positive. So keeping that in mind, I don't really even need to calculate anything. I know which one of these tables, this this -3 goes with this over here. Oh, not -1. The magic of computers. -3. Let's see what it does with that. Ah, there we go. Versus this is the positive 3, the slope, positive. So I don't really have to calculate anything, but to be on the safe side, I could check. Again, you can use any 2 points you want. Say take that point and this point. They're very large, but those points fall in the grid. I'll just see rise over run. So rise 6, run 2. Well, rise over rise over run. Hold on. Anyhow, rise over run 6 over 2 equals 3. So that confirms this is the correct slope, 3, for this line. And over here on the left side, we can confirm that that slope, so we could even do different points. We could take this point right here and this point right here. If you can see that. It's down 3 and over 1. So down 3 over 1 is that -3 over 1. -3, down 3 over 1. That's our rise over run. So we get -3. If we scroll further down, we've got the equations. We can see here, let's see if we can find Magic pen. Nope, I don't want the magic pen. Creative pen. And stars. Let's use stars. Right here, star. This line intercepts the y-axis at 6. And this line also intercepts the y-axis at 6, which explains why the y-intercept, when we look at those equations down below, both say plus 6. You can see that right here. Both of them have plus 6. Remember, that's the y-intercept. We looked at that. We looked at that right here. That plus b is the y-intercept, where the line intercepts the y-axis. Here we go. All right, so we can then take a look at the other parts of the equation, which were m, where we see the slope is listed right here in front of the x. We got 3 and negative 3. So once again, we can see what very easily matches up. And this page is kind of nice because it shows you how you can find slope from tables, graphs, or equations, and how all three things are connected and relate. Ooh, I'm doing quite a job over on the margin here. Oh well. Moving along. Over here we've got equations for some situations here. There's memberships going on. Let's see here. Okay. Yeah, so sorry, this is like the third time this program's crashed on me while I'm trying to record. Okay, so we got members. Members at this golf club are paying $100 a year plus $7.50 a game. Non-members are paying $15 per game. There's no annual fee. The story problem down here tells you that we're going to call the cost for this group C1 and the cost for this group C2 or C sub 2, C sub 1. So got that. Oh, they tell you right here. I used the wrong color. Oh well. Yeah, I was going to be fancy and match them up. Here we go. Got yellow for the members. Every game of golf is a G, and then the non-members are listed here as C2. They also tell us that we are going to, they tell us here for both tables, run G from 0 to 50, increments of 10. So that was nice of them to help us know what to do here. So we're going to do games that they play, and this will be the cost for the members. This will be cost for non-members. They told us to do 0 to 50 in increments of 10. So we'll do that. The members, and then this is just to kind of keep things straight. And feel free anytime. I mean, I think it's great if you have highlighters, colors, you want to write notes, anything that helps you. You might be amazed sometimes at what a little bit of color coding or labeling or writing down some fact will help keep your mind on the problem and keep things straight in your head or give you a direction. All right, so these are the members, the yellow group, the cost for those people, and they are the ones who have to pay a $100 annual fee. Even if they don't play any games, they have to pay $100. Now, we know that they pay $7.50 a game, so if they play 10 games, 10 times $7.50 is $75, so that would be $175 total that they would pay for that year. If we then go on, they keep increasing by 10. So I know that every set of 10 games is $75. So this would be $250. This would be $325, $400, and then $475 for them. For the non-members, the green group, their cost, if they don't play any games, they don't have to pay anything. If they play 10 games, we know they're paying $15 a game. So 10 times 50 is 150. And then that continues all the way along. So it's 150 for every 10 more games. So then this would be 300, and then a 450, and then 600, and then 750. Okay. All right. Down below, they ask us to graph the relationship of the cost and number of games for the members and non-members. So I'm going to use yellow for the members and green for the non-members. And the grid lines here, let me see if I can come up with a label quickly. Here, I'm going to pause this and do this so you don't have to sit and watch me do it, because it's a pain in the neck with this tablet. Just a second. Okay, there we go. That's a little better. What seemed like an instant to you was about a 6-minute ordeal with the smartboard and tablet. But anyhow, I've labeled the y-axis and the x-axis. Since our number of games, well, the number of games, of course, is going by tens, 0, 10, 20. So what we'll do is we'll just we'll pretend that on the bottom each one of these represents 10 games. So where it says 1, that's actually 10 games. Then we have the cost going up here on the y-axis. What you have up top here, and what a lot of people don't think about, is that really these are just ordered pairs. These are solutions to the equation, to the equation, to the situation that we're working with. So we can consider each one of these an x. Oh dear. Okay. Well, hold on. Okay. Let's try this again. Okay, I can't remember where I was with the recording, but I'm going to be. Oh yeah, I was talking about these things being the same thing as ordered pairs. What you really have is x and y, x and y. Each one of these things, each game and cost, or number of games and cost, represents an ordered pair, just like what you've seen in the past many times before when you've graphed anything. So I'm going to take this ordered pair. We'll start with this one, 0 and 100. If we go down to the graph here, I'm going to use, as I was saying, I'll use yellow. Here, let me shrink this down a little bit. Maybe we can. 100. Okay. Yellow. Okay, 0 and 100. Okay, 0 over 100 is right there. Oh, we can't see it. It's right there. And then 10, 175. But you don't have to graph every single one of them. You really only need 2 points to make a line. Maybe we'll graph 3, though. I'll try, say, 20 and 250. So 20 over and 250 up right there. And then maybe I'll do the 50 and 475. So 50 is over here on my x-axis and go up to 475 on the y-axis. And I'll put a point up there. Okay, and then we'll connect that with a line in just a second. I'll graph some green ones now. The green, these, they don't have a y-intercept. They start right there at the origin at 0, 0. 0 movement on the x, 0 movement on the y. Then we have, say, 10 and 150. So I could graph that, go over 10 on the x, and go up to 150 on the y. Put a point. And maybe one more for good measure. I don't want to go off my chart. Say 30 and 450. So I could go over to 30 and let's see, where is this? 30 and 150. Okay, so we have a point now at 30 and 450, which I again used green. We'll zoom in a little bit on this. We'll go to 150. Okay, and let's connect with lines. We'll do for that one, and we can do green for the other one. Maybe. Okay. Again, half hour later and like 3 crashes afterward. I had to redo this. I don't know how many times. Anyhow, I've got the 2 lines graphed. The members are the yellow, or is the yellow line, and the non-members is the green line. And we've graphed them both using just 2 or 3 of the ordered pairs from the tables above. That's all you need. You could graph them all if you wanted to, doesn't matter. All the points will be on the line, assuming you did your tables correctly. And now what we have too is this intersection point. This represents a solution for what later they'll call a system in 8th grade. They'll call this a system of equations. This point is the solution for that system. And it's a rather important concept, but it's dealt with more in 8th grade than anywhere else this year. So, on the symbol graph, blah, blah, blah. All right, so just FYI, well, let's see what questions they ask about us, about this next. Forgive me, it's almost 1:30 and I can't think clearly anymore. Here we go. The equation, okay, write equations you can use to calculate the cost for members of C1 and non-members C2 for any numbers of games G. Okay, we can do that pretty easily. Assuming, oops, yep, it's still right. Okay, for members, we know that the cost, and we'll just call it C sub 1, but the cost is $7.50 per game times G. So you pay $7.50 times whatever number of games, plus they have that $100 membership fee. The cost for non-members, C sub 2, is simply $15 per game, and you're done. What is the slope of each line in part C? Remember that we have this written in y equals mx plus b form. They are a linear equation. We know that from graphing them on the prior page. If they are linear, we can look at the slope-intercept form, and we know that the coefficient of g, right here, the $7.50 and the $15, represent the slope. So the what's the slope for the equation of members? $7.50, and for non-members, it's 15. What does the slope of each line represent about the membership and non-membership costs? It represents, the slope represents the cost per game. You get $7.50 for each game for members and $15 for non-members. And it says, explain how you can find the slope from a table, a graph, and the equation. Looking at the equation, we can find it because it is always the coefficient, or it sits next to the x variable, or in the case of this story problem, it's sitting right next to g. It's the coefficient of g. So we can find the slope from the equation that way. From a graph, we can do rise over run. And from a table, we can do the change in y over the change in x, which we could find up here too if we wanted to do that. Again, you could look at this as being x and y. The change in y each time, they're constantly adding 150. The change in x is adding 10 each time. So the change in y over the change in x is 150 over 10, which 150 divided by 10 is 15, which is what the slope is 15g for the non-members. So we see that slope appears here in the equation. It appears in the table. We can calculate it from the table. And if I want to do rise over run, which right now this hour I'm just too tired to do it, but we could look at the non-members, I think. Let me see. What the hey, we've come this far. Let me try it. And no guarantee how accurate this is any longer. I've been doing this I don't know how long now. But say we did rise over run. We go from 300 to 450, so it's 150 over. I'm counting by fives, so it's the run is 510. So there we go, 150 over 10. It's 15 there. So it appears in the table that way, rise over run. So no matter which way, any way you slice it here, whoops, went too far. Table is change in y over change in x. Graph is rise over run, and the equation is just to look at the y equals mx plus b, and look for the m, look for the coefficient of x. I think, oh, there's more questions. What does the y-intercept of each line represent about the membership and non-membership costs? Remember, the y-intercept is representing like the head start that well, in this case it's the extra fee that they have to pay if you're a member. So they, in terms of cost, they start off with a cost of 100 versus the non-members who do not. For what number of games will the cost be the same for both members and non-members, and explain how you found your answer. We could calculate, if you wanted to go to the equations, you could do some guessing and checking to find out what could we multiply 15 by and $7.50 by plus 100 to get the same cost. At what point, what numbers would get us there, what number of games. But that would take a lot of guessing and checking with the calculator. At this point in time, probably what the best or easiest solution for us to do, although in this case would be not the most accurate, because it would be the intersection point that represents for a certain number of games. It looks to be about 13 or so. The cost is a little less than 200. So that would have to be our estimate. Reading the graph, the intersection point of the two lines would represent the solution to that set of or system of equations, and would tell us that. Where did that question go? Yeah. At that point where the lines intersect is where the cost is the same for the same number of games. And that's about it. And it's been, let's see, 38 minutes long, and it's 1:30 in the morning. I think I'll call it a night, and hopefully this actually recorded with sound. That would be ironic if it had no sound. I'll play it back, hope it saves, and post it. Have a good night. Bye-bye.